LANs, when they do have constant voltage sequence being transmitted. Design goals, they have no DC components and have no long sequence of zero level line signals. They also don't have reduction in data rates as well, because we're maintaining the length of the original message across board, and to maintain that some of these things are false, and the design. And he also gave the goals of the design to address error detection needs or error detection capabilities within a system. These you'd find in a number of telecommunication systems, especially CDMAs within the European market, within the US market. CDMAs very popular, where you embed codes or you scramble the signals for a given transmitted information or data in order to be able to identify the sequence of the information and interpret it properly. So various interpretations of the two main techniques that we have. So here we have it, since the sampling uses the bipolar from the multi-level binary techniques. To illustrate it, we have a bipolar AMI signal with a bit sequence of 1 1, and then you have a whole bunch of zeros, because we're going to address these zeros, especially within a long distance transmission. We're going to address that issue. And if you notice, within a bipolar AMI, ones alternates, high, low, zeros are usually level, ones alternate, high, lows, or low, high, depending on where the sequence is of that particular signal bit. Now, when it comes to the bipolar 8-0 sequence, since it's still adapting the bipolar, we have the high lows for the 1 and 1 transitions with a 3-level binary. Now, when it counts, when you notice the sequence that comes after the first 2 or first 1 bits is a representation of just no voltage pulses, a sequence of 0, then you need to figure a way to adapt, to incorporate various codes to inform the signal that we have a sequence of zeros being introduced within transmission. And here there are usually 8 zeros that incorporates that. So if you look at it, you have 1, 2, 3, 4, 5, 6, 7, 8. The 8-bit sequence of zeros. And we don't want to have it fluctuate at 0 level or at the level pulse. So with the very moment notice, the system noticed that within a sampling, what it does, the first 3s are kept level, and then subsequent bits are embedded with the codes to indicate that, okay, we have an 8-bit sequence of 0. So our first 3, after the first 3, we have to transition the bit, okay, to indicate that we have a sequence which could be an interference or an impedance on the particular given signal, or a signal that's being carried over a longer distance with voltage absent, or with an absence of voltage within that 8-bit sequence that you have with zeros. So after the first 3, it's the voltage code, the codes the sampling codes that are incorporated. You have VBs indicating that you have the a violation. Exactly. So usually the term of violation when you have a sequence of 8 of no voltage presence. So V represents the violation, and then B represents a valid polar signal, valid bipolar signal. Okay? So we say after the first three, and you still have a number of zeros coming up in that 8-bit sequence, we say it's a violation after the first three. So we introduce a level pause, and then move to a positive or a different state to indicate a valid voltage pulse, and then a 0 to indicate a standard voltage transmission, and then vice versa for to address the 8-bit sequence of zeros that was indicated within the transmission. So your violations and your validities are all factored into designs. Now, if you notice, if you look at this on this side over here, we had 1, 2, 3, 4, 5. These falls within the 8 bits, or they're not over the 8 bits. Sorry, they're not more than 8. Sorry, they are not 8 bits in sequence. They are less than 8. So hence we maintain the bipolar AMI, or the multi-level concept for the zeros as level bit sequence. So usually the embedding of the violations or the codes for violations or validity of a given signal within the scrambler, it's usually called upon when you have 8 sequence of zeros of no voltage presence. So keep that in mind, it's only at that point. And then the high density bipolar 3 zeros has got its own representation as well, especially when it comes to the 8-bit sequence 2. So the same thing is a violation. That's a valid one, and then we just form the same. We just go by the main or the usual form of a bipolar AMI, the zeros, and then we represent them. Whenever we incorporate the violations at the last 0 bits that we have. And then you just come back to your usual highs and lows signal representations for standardized bipolar curve. But I should point out that with the high density bipolar with 3 zeros, it usually applies when you have 3 zeros in sequence, as compared to the 8 zeros where you have the violations come out. So the first 3 zeros is a violation, a valid code, a standard bipolar. 2, the third 0, a violation, and your usual bipolar AMI. So yeah, you just got to look out for the 3 zeros for the high density bipolar 3s, and then the bipolar 8 zeros. Just looking out for the 8 zeros sequence, and then you just have your violations embedded in the sequence that you have following some of these illustrations of the encoding. So another word to use for those variations in terms of the embedded sampling of code, it's the polarity, it's the polarity. So for odd ones, you have 0, 0, a minus, a plus, a 0, 0 plus. And even is plus 0 plus, and for the plus at the A substitution level, you have a minus 0, 0 minus. Okay, this is a bit confusing at some levels, but like I said, if you were to basically start practicing on a regular basis, you start seeing where uh, these manipulations of your uh, bipolar AMIs falls within the 8-bit sequence of zeros or 3-bit sequence of zeros. Pros for the scrambling techniques, quite effective for long distance transmission, as we mentioned earlier, and cons or disadvantages, it's less effective at short distance transmissions. So when we talk about transmissions from 0 to 10 megabit per second, they are quite less efficient, which are short distances transmissions. They're very, very less effective. And this way, you actually adapt uh, the biphase techniques instead. Or this where the biphase becomes much more efficient for shorter distance transmissions. So a summary of that, the various encoding techniques within the groupings that you have. Okay, great. Now let's move to the other phase of the encoding transmission, which is uh, the modulations, where we're basically moving from a digital signal or a digital data to analogs. And this is where we need modems to help, with some of these uh, challenges that might come up. So at this point, we're going to be talking more or less about modulations. It's part of encoding techniques, but at the modulation level, where we're dealing with two separate forms of signal, digital and analog. So as we mentioned earlier on, um, both analog and digital data can be encoded as either analog or digital signal. Okay. Um, so we've already gone through the encoding part. We dealt with a lot more of the digital part of it, digital signaling. Now let's look at the analog part. So when it comes to analog part, we want to encode um, digital data into an analog signal. We need a modem to help us with the conversions, which is uh, moving from one transmission form to another. The basic encoding techniques used here include, or the basic modulation used at this level of the technique, of the encoding techniques, is or includes the amplitude shift keying, or ASK for short, which is a modulation technique. We also do have the frequency shift keying, or FSK, and then we have the phase shift keying, or PSK. Now, all of these modulation techniques, it involves altering of one or more characteristics of a carrier frequency signal to represent a binary data. Since we're converting from digital data to analog signal, we have to figure a way to make sure that we maintain the digital representation of it at the other end, or at the other end, and also maintain integrity of the information being transmitted. So carrier Frequency signals needs to be able to manage that very efficiently so they don't lose uh, the signal integrity. Okay. Now, analog data conversions to either digital or analog signal transmission generally requires modulation. That's what I said. We just pointed out earlier. Modulation is usually the process of varying one or more properties of a periodic signal wave form, or in other words, a carrier's frequency signal. Generally, analog data such as voice and videos are often digitized to be able um, to use it within digital transmissions facilities. The simplest technique used for mostly um, handling analog data to digital signal transmission is the pulse code modulation, which involves sampling the analog data periodically and then quantizing the samples so you can be able to digitize it much better for a given application that you need. Okay. Um, so anyway, within the three modulations techniques that we have, they're mostly used within public telephone systems. The with frequency ranges from 300 Hz to about 3,400 Hz, and they usually require modems to help modulate it and demodulate it from given ends of a given uh, system implementation. So here is what a modulated digitized data to analog signal will look like. So at the top we do have a number 10 to 0, and this would probably be the number 10 to 0 level technique here, and we want to interpret it, or we want to convert it into an analog signal uh, using an amplitude shift keying. So we look at it carefully with the zeros indicating no voltage pulses. A 1 have got uh, an, an amplitude signal pulse of high, lows, and high. So in this case, we have three levels of voltage amplitude here. Here we want amplitude. Keep that in mind. It's amplitude, not necessarily the voltage levels here. So in terms of amplitude, we have for 1 we do have 1, 2, 3. Okay, or should I say 1, 2? If you were to put all of that together, you have 1, 2, 3, 4, because there's 2 at the positive voltage level and 2 amplitudes at the negative level. The amplitudes here are just the signal level fluctuations that you would have, the change in the signal levels, or what you term the modulation rate. Remember, in the earlier terminologies. So once, let's keep them once will always replicate itself in signal level changes in twos at the positive and negative levels. So hence the reason why you do see the ones having the twos for both positive and negative. Zeros are always represented by no voltage pulses, and so forth and so on. when it comes to the frequency shift keying, S0 have got only two amplitudes here, or frequency levels for the zeros, whereas the ones to maintain their four. In other words, from both positive and negative. But for zero, it's just 1, 1 on the positive and negative levels. So for frequency, you just have 1, 2 for zeros. Once you have 1, 2, 3, 4. Just maintaining the original state from the amplitudes for the ones. And then the phase shift keying can get a bit interesting in its implementation, in its signal formation. You do start with a low voltage for zero, a low frequency or a phase shift, a low phase shift to start with, and with an amplitude of 1, 2, 3, 4, involved for zeros, the same, 1, 2, 3, 4, and then for ones, the usual 1, 2, 3, 4, and it just keeps going back and forth. All that you need to understand is that zeros start from a negative phase of the signaling, whereas one start with the positive. Okay. So digitization is conversion of analog data into digital data, which can then be transmitted using either a non-return to zero level transmission encoding scheme. So usually analog data to analog signals are modulated by frequency carriers to produce an analog signal in which frequency or different frequency bands are used, which can be either utilized on an analog transmission system, and the basic techniques that are adapted for amplitude for some of these transmissions falls within the amplitude modulation or frequency modulation and then phase modulation, which basically is what we've talked about earlier on within this three phases that we have, or within these three modulation techniques that we have. Okay, so the modulation part of it is what we term the amplitude modulation, frequency modulation, and phase modulation. They produces some of the modulation techniques that we have for the amplitude shift keying, frequency shift keying, and phase shift keying. So when coming back to digitization conversion, when a signal is transmitted using codes, especially when it comes to digitizing the data signal, you can embed codes other than just non-zeros, other than just the non-return to zero levels, depending on how the digitization needs to be applied within a given application. You can also convert the analog signals back and forth. So here we're looking at just converting the signals from analog form to digital. And usually that requires just going back to your encoding techniques, because now we're moving from analog to digital. So once you have the analog data, we digitize it through a digitizer. And then after modulating anyways, after you modulate first, and then you just adapt the encoding or encoders and decoders in the process using either the non-return to zero levels or the other encoding technique we have to help you interpret the signals. So we say analog to digital conversions are usually done using codecs, like you'd have in a number of video signaling codecs for various samplings that you have for a given application, using the passcode modulation. And then other one is the delta modulations. So in the picture X format, if you wanted to convert an analog data to digital, you digitize the signal by running through a digitizer, okay? Either a passcode modulator, whatever you have, and then you apply an encoding techniques to it to give you the digital data form, and then you modulate it to give you the analog data on the other end of the spectrum. So in this scenario, you have a voice coming through, just regular voice, and it needs to be digitized into a system because you, assuming for instance, this were to be your cell phone, you're talking on your cell phone. Your voice goes into the cell phone, and you do have these pulse code modulations that will digitize the voice that you're speaking into the handset. And then it applies a number of encoding techniques to turn into a digital code of having your ones and zeros or your binary sequence that you need. And then when it's going out of the cell phone to the receiving end, okay, it goes to modulating devices that will basically modulate it and demodulate it, okay, and in a format that's much more constant. It's not erratic, so it maintains the integrity of it using any of the modulation techniques that you have. So it can be fine-tuned for the other user to receive the information as it was transmitted in its raw state. So we talked about modulator carrier frequencies with analog data and why modulate. So a question that we usually have, most people usually have is why modulate an analog signals? Well, for higher frequencies, so you can give more frequency or so you can allow more efficiency within the transmission. One of the reasons why you modulate analog. So, if you were to just pass your regular voice and it's erratic or irregular signal waves, it wouldn't be efficient for the transmission. So ideally, modulation does streamline a number of those things, so the system can be able to interpret it much better and handle the transmission much more efficiently across various modulation techniques and within a given transmission media. Another one would probably be to permit frequency division multiplexing, which is usually adapted within various multiplexing techniques you'd have, either time division or frequency division to multiplexing, which means the combination of a signal for transmission across a given medium. Types of modulations that we have, I think I already talked about those. We have the amplitude, we have the phase, and then we have the pulse modulations. So here are the various